Hello everybody, this is Jeff Janess and welcome to our 7th lab exercise on creating and editing data. In this exercise we're going to see how to georeference an image, and there's lots of times you might have an image you want to turn into real spatial data. And for this example we're using some old GLO General Land Office maps from the 1800s of the Flagstaff area. I just downloaded one from the BLM site where you can get these, and if you are interested, I've got the link in the lab exercises. Just go to this site. You would search for some township and range and hit search, find some old survey. So this is one that was done back in 1895, and they're pretty cool. They're kind of fun to look at. They give you a real sense of the history of the area. All right, but we're going to be using this exact one in this lab exercise. So let's get started on it. First, we're going to load up the public land survey polygons for Coconino County. If you ever heard of the township section range system, that's what this data comes from. If you ever heard of coordinates referred to as the northeast corner or the southeast corner of section X or whatever, that's what this data is from. So these are all the township range polygons for Coconino. We're going to also load up some USGS topo maps just because those make a nice background. Now if you still have your connection that we set up in the data types lab, you can find this USA topo maps in that connection, the ArcGIS Online. If you don't have that, then you can also get it in the portal section. Go into ArcGIS Online and just typing USA Topo Maps here. We'll pick this one. They both look the same. And also I'm going to set my map coordinate system to be UTM Zone 12 just because I think that might make some of this lab exercise work a little better. Okay, now let's load up this old survey map from the GLO office from the 1800s. Just hit Add Data. I've got it for you in your Selecting and Creating Data folder. It is this one. AZT22NR7E means it's in Arizona. It's Township 22 North and Range 7 East, surveyed back in 1896. The Township Range section divides up the land into what they call townships, which is a 6 by 6 mile block, and within that there are 36 sections, each of which are roughly 1 square mile in size. And so this is one full township. This is the area that includes most of Mount Eldon and the southern part of the San Francisco Peaks. Schultz Creek, Schultz Pass goes right through the middle of it. Now this raster doesn't actually have any spatial information with it, unfortunately. It's just an image. So when we load it into our map, ArcGIS doesn't really know where to put it. If we zoom to the layer, basically it puts you at the origin of the coordinate system that your map is in. So we're in UTM Zone 12 right now. Zoom to this layer. Put our mouse down at the bottom left, we see the coordinates are right about near 0 and 0. So this is the 0 point, the bottom left of the image. Now let's zoom back to the Coconino County here. Now this image is from Township 22 North, Range 7 East, and that's included within Coconino County. So what we need to do is just set a definition query on this Coconino County data so it only shows us Township 22 North, Range 7 East. So let's do that. It's in the layer properties. Go to the definition query. We're going to get a new definition query where township is equal to 22 North. That's this one. And range is equal to 7 East. And that's this one. Hit apply, hit OK, and there it is. So this is where the image is really intended to be. So let's zoom to that extent. Let's change the symbology a little so it'll be easier to work with. We'll go to symbology. I'm going to change the symbol to hollow, and I'm going to change the color to red. It'll just make it pop out a little bit easier. All right. Now you might notice that in the USA topo maps, you get these same section lines back here, and they're pretty close to the vector data set we've got loaded up. The vector data set divides it into quarter sections, not just sections, so that's why there's more polygons there. Next up, we've got to start georeferencing our image. So first we select our raster layer here, then we go to the Imagery tab here, then we click on Georeference, and this will take us into a georeferencing session. Hit OK, and now we're there. We'll keep doing it until we're done, and when we're done we'll hit Close Georeference and it'll take us out. But in the meantime, we are ready to start working. We got a little report here that's given us a running accuracy and error level of our current transform, and we haven't done anything yet, so it's all in zeros. I'm going to click this little thing to kind of scoot it out of the way a little. Alright, so first off, what we do is we're working on this raster layer, and we have to fit it to display. This just pulls it from wherever it is and fits it in the middle of our map. So it's a little bit easier to start working with. Now we're going to start building ground control points that match up a point on the image with the background reference data. So we're going to start with this one up here, up in the northwest corner. I'm just going to zoom into this spot here. So this right here is the corner of section 6 in Township 22 North, range 7 East. This is the northwest corner in the image, and this is that same spot in our reference data. So this is where the point truly is on the ground. This is where it is on the image. So we have to basically drag it up there. We do that with these control points. So I said add control point. I first click on the image, that's at this corner, and then I say where this is in the true world, and that's right up here. I've got my snapping turned on, so it will snap to the vertices of my Coconino PLS data. Hit OK, and it drags it right up there. So we're on our way. But we got to add lots more control points, and so I'm going to zoom out to the extent of our vector data. And now I'm going to go down to this point down here. Okay, I'm going to zoom into where I can see the corner in the image and the corner in the vector data set. So that here it is in the image, and here it is in the vector. So I need to bring that image down to that corner. Don't forget about your panning and zooming tools. They'll really help here. So I'm going to first click on the image. I'm going to zoom out a little bit, pan down to my corner, and it snaps right to it. So I hit OK, and it enlarges my image. It stretches it to fit that corner. Okay, let's add a few more at the other two corners. It looks like it's fitting pretty well so far. This is good news. So let's go down to this corner. Looks like the image corner is right about here. The true corner is down here. Okay. Let's go back to our previous extent. Let's zoom into this corner up here and get this last one. Okay, now notice that fourth point that I added, it wasn't able to perfectly align these two. And that's just the nature of having a affine transformation. The default transformation is that first order polynomial, which is affine. All that does is stretch. It doesn't bend it at all. It just stretches it and skews it. And when you have that transformation, it's very, very difficult to have 4 points and have them all be able to be transformed perfectly. But anyway, if we zoom to the extent, we've now got it pretty well in there. It's matching really well the vector boundaries of the sections. So that's all good. We can open the control point table and get a sense of what the error is so far. This control point table is really handy. So I've made 4 ground control points so far. They have a residual error over here. This residual error gives you a sense of the general error of your transformation. The transformation does a best fit from the control points you give it. And that means that all the points will have a little bit of error to them, that root mean RME error. This means for ground control point 1, the coordinates we got on the image are about 20 meters off. Number 3 here is 21 meters away, so they're all not too far off. If I had one that was really out of line, it would really show up here with a high residual error. And that would let me even uncheck it and get rid of it if I wanted to. Now, with 4 points, we're kind of limited in the transforms we can do. We have the first order, and then there's these others that are just kind of interesting variations. But if we wanted to get to, say, a second or third order, we would have to add several more ground control points. And that's not a bad idea in general. So I'm going to add 16 ground control points total, and we'll see what the errors start looking like. So put one here. Okay, now I have 16 ground control points. Let's take a look at our table. Looks like our overall root mean error is about 38 meters on average. So I can look at the errors of the individual points here. I can even sort them by which has the most error, and I can see that point number 6 appears to have the most amount of error of all. I can uncheck point number 6. Right now we got a total of 38.8. If we uncheck number 6, then our average goes down to 35. So maybe point 6 isn't really contributed to anything but extra noise. Well, you never know. But this is also just the first order transform. So now we have enough points we could try a second order. Remember, that adds a single bend into the system. It drops our total error down to 34. If we went for a third order, that drops our error down to 23. So that might be good, but it's always good to look at the map as well. Sometimes these transforms have good numbers, but they don't really look good when you look at it. But this is all looking okay. If I took out number 6, it would all shift a little bit. We'd have a lower error here, but I don't really like how it's getting shifted up on these up here. So I want to turn 6 back on. I think it's a better transform with it in it. So I would probably go with this third order. Sometimes when you have an odd kind of image that really doesn't smoothly transform, there's an option that this spline option is pretty nice. It makes sort of a local transform around your ground control points, and it forces the raster to fit perfectly at all those points. And for something like this would probably be a better option. It kind of messes up your error analysis because since it forces everything to fit locally, you have 0 residual errors. So that information is kind of gone. But this would allow me to fix some other spots. Like these old survey maps often had odd error in them. People were out there on horseback trying to map these things, and they didn't quite get it right all the time. So right here, I could just add a couple more and force it to all squeeze in there better. Here's one up here that's a little bit off. Okay. So we get a little bit better. We can spend as much time as we want on this. In the meantime, I think this is a pretty decent georeferencing of this 120-year-old map. And there's almost certainly as much error back in the original mapping that it's washed out by any errors that we're introducing in our georeferencing. So I feel pretty comfortable with how this is looking right now. So the next step would be to save our georeferencing. There's 2 ways to do this. First off, we can do save as new, and this is the better method for if you want to do further work with this raster, if you want to do geoprocessing tools on it or something later. This produces a brand new raster that is a georeferenced version of the original. So let's do that for now. Okay, we say where we want it to go. I'm just going to put it in this. We don't want to put it in our editor lab, so we'll just put it here. We're going to call it test georeference. This is an awful lot of columns and rows. I'm gonna say I want the cell size to be 3 meters by 3 meters. This is the cell size of the current coordinate system. I don't want it to be in geographic coordinates. I want it to be in the coordinate system UTM zone 12. Okay, at 3 meters by 3 meters. That'll give us lots of rows and columns. 8-bit unsigned is a decent one for this. This means that it'll store numbers between 0 and 255, and that's what we got going so far. Okay, we want to set the, go to settings here. We want the resampling to be bilinear, and we're going to build pyramids for it so it loads faster, and we're going to use bilinear for the pyramids as well. Okay, that should be enough. We hit export. Goes to work. All right, all done. And we turn off the original, turn off these, and this is the true georeferenced raster now. It loads up right in the exact right spot where it ought to be. So it is now true spatial data, and we can work with it. Now I wanted to show you this other method though. We saved a new raster. There's also this one called save. Save is kind of interesting. It doesn't do anything to the raster itself, but it does save all your transformation information into the metadata. So if we hit save, then it doesn't ask us any questions. It just does the save. And if we go look at the files in Windows File Explorer, this is Windows File Explorer. Here is the raster we've been loading. This is the actual raster. These are the pyramids that make it draw faster. This XML is the metadata. So when we hit save, it wrote some stuff into this metadata. We're gonna, if we take a look at it in Notepad, Notepad++, we'll see this is the basic metadata, but we scroll down, we start to see all the ground control points, source GCPs, that's ground control points. So these are all the ground control points it used. And this means that it's able to perform a transformation on the fly when you load it into ArcMap. So the data is still unchanged, but ArcGIS Pro is transforming it, it's kind of recreating it in your map in the right location. And it's kind of a handy little thing. That also produces this TFWX. Remember we talked about world files? So it creates this world file as well. Just tells it how to place the image on the map. So the data, the TIFF file itself is unchanged. It's still the normal TIFF file. ArcGIS Pro is redrawing it when it brings it into the map. All right. So we have saved it 2 different ways. Now we're going to close the georeferencing, exit the session, and it all looks good. So we now have data. Sometimes it's kind of fun to compare these old maps with modern maps. We can set the transparency a little bit down. Zoom into some areas here. Like the old map had Humphreys Peak sitting right here. Modern day Humphreys is actually way over here. But it could be they were just looking at Fremont Peak here and calling that Humphreys. You know, this was a long time ago. They did not have the tools we have today. So kind of interesting. Okay, for your homework, you're going to want to zoom to this layer. And you just want to take a screenshot of this and paste it into your homework document and turn that in. All right, thanks so much, everybody.